Welcome to this explainer. Today, we're diving into a structure that most of us completely take for granted, even though it's an absolute masterpiece of biomechanical engineering. Presented by Dr. Christophe DeLong and Conexa Formation, this breakdown is going to make you view your own footsteps in a totally different light. Get ready, because we're deconstructing the precision machinery that actually allows you to stand, walk, and run. Let's dive right in with a mind-blowing number: 7,000. That is exactly how many nerve endings you have packed into a single foot. Your foot isn't just a block of bone and flesh smacking the ground. It's literally an ultra-sensitive antenna. It's a high-resolution sensor constantly scanning the surface of the Earth. And honestly, that's just the tip of the iceberg. So here's our blueprint for today. First, we'll look at the engineering marvel itself. Second, the bony foundations. Third, we'll check out the joints and mobility. Fourth, the muscular engine driving the whole thing. And finally, we'll unpack that incredibly complex sensory network.
All right, part one, an engineering marvel.
You know, when you hear complex architecture, your brain probably goes straight to skyscrapers or massive suspension bridges. But seriously, just look down at your feet. In such an incredibly restricted volume of space, nature has condensed 26 bones, 33 joints, and over 100 muscles, tendons, and ligaments. It's this dynamic assembly working in absolute perfect harmony. With every single step you take, this entire system compresses, absorbs shock, reorganizes itself, and then propels you forward with ruthless efficiency. Moving right along to part two, the bony foundations. This underlying architecture is beautifully divided into three distinct zones. You've got the rear foot, the midfoot, and the forefoot. Think of this as the heavy-duty chassis of your bodily vehicle. And here, form completely follows function. The rear foot features the heavy tarsal bones, like the heel, which handles the massive static weight when you're just standing around. Moving forward, the midfoot acts as your primary shock absorber. In fact, the first metatarsal alone takes on a whopping 50% of your body weight during propulsion. Then finally, the forefoot and its 14 phalanges act like a built-in pulley system to launch you forward. It is just a brilliant distribution of force. Which brings us to part three, joints and mobility. So how does that rigid bony foundation adapt to a rocky trail or a slanted sidewalk? Well, it transforms into an all-terrain adapter, thanks to 5 major joints. It's basically a mechanical sequence. First, the ankle lets the foot move up and down. Right below that, the subtalar joint manages your side-to-side tilt. Then comes the real magic, the mid-tarsal joint. It can literally lock into a rigid lever for pushing off, or unlock to absorb uneven ground. Below that, the tarsometatarsal joints provide that essential stiffness right before push-off. And finally, the joints at the base of your toes allow them to bend upward at the exact millisecond we leave the ground. It's a split-second symphony of locking and unlocking over and over again. Let's shift gears to part four, the muscular engine. The raw power generated by the muscles in the back of your leg is staggering. Get this, the Achilles tendon alone can support a phenomenal load of 450 kilograms. That's almost half a ton of capacity. During a normal, everyday walk, it generates between 500 and 800 newtons of force. You're basically housing industrial-grade suspension cables right at the back of your ankle. But here's the catch. This engine isn't only built for explosive strength. Look at this breakdown. Notice the overwhelming dominance of type I, or slow-twitch, muscle fibers. They take up about 75%. That means your foot is fundamentally an endurance machine, designed to maintain your posture for hours without burning out. Only a tiny 5% fraction is reserved for those explosive, very fast efforts, like if you suddenly have to sprint to catch a bus. And the way your body manages this power, it's pure computational genius, all dictated by Henneman's size principle. Basically, your body always recruits energy in the most economical way possible. It fires up the small, highly efficient motors just for standing posture. When you start walking, it seamlessly triggers the medium motors. It only ever taps into those heavy-duty, energy-hungry, explosive motors if you actually need to jump or sprint. Your foot automatically scales its power consumption to match the exact demand, instantly. And finally, part five, the complex sensory network. Remember those 7,000 nerve endings we talked about at the very beginning? Well, this is where that massive armada of sensors comes into play. The foot isn't just a mechanical tool, it is one of your major sensory organs, constantly feeding your brain exact, real-time data about the terrain below. You can really think of these receptors as high-tech environmental tactile sensors. You've got Meissner corpuscles catching light vibrations and fine textures, then the Pacini corpuscles, which run a bit deeper, detecting high frequencies and heavy pressure from things like rocks or uneven dirt. Merkel discs measure static pressure, so you instinctively understand the shape of what's underfoot. And Ruffini endings? They detect skin stretch, instantly firing off a warning signal to your brain if your foot even begins to slip on a patch of ice. But the data gathering doesn't stop at the skin level. Deep inside, you have these incredible proprioceptors called muscle spindles, acting as internal telemetry sensors. Implanted right inside your muscles, they measure the length of the muscle and the speed of its stretch in real time. This continuous data loop enables your reflexes to adjust your balance in space in a fraction of a second, with absolutely zero conscious thought from you. So what does this all mean? Well, after tearing all of this down, after seeing the flawless synchronization of 26 bones and 33 joints, the literal industrial lifting capacity of the Achilles, and the real-time data analysis of 7,000 microscopic sensors, it kind of changes your perspective, doesn't it? The next time you tie your shoes, realize that you aren't just covering a limb, you are housing a biomechanical supercomputer. Thanks so much for joining me for this explainer, and we will catch you next time.